Hello everyone! Today we're going to learn all about graphing functions. We're going to go ahead and actually start with graphing polynomial functions. In order to do this, we need to review a few things that we've been learning over the past couple of weeks, in addition to the previous semester of algebra and what we've learned about polynomials so far. We're going to go ahead and call all of these things part of our polynomial graphing toolbox. Let's go ahead and get started. The first thing that we know how to find when it comes to polynomials are the x-intercepts, also known as roots or zeros of our function. Methods we have learned for finding the x-intercepts involve factoring, the rational root theorem, combined with the factor theorem and synthetic division, as well as Descartes' rule of signs, which can help us determine the nature of the solutions. Another important thing of polynomials that we have learned how to find in the past is the y-intercept. Remember, in order to find the y-intercept, we plug 0 into our function, or we find f of 0. Now, we do have two new things that we are adding to our polynomial graphing toolbox that will help us as we learn how to graph polynomials. The first thing that we're going to learn about is called interval behavior. This is basically what happens between each x-intercept. This leads us to one new term, which is called a turning point. A turning point is when the graph changes direction, either from increasing to decreasing or from decreasing to increasing. Think about your quadratic functions that we've been studying. When do those change direction? That's right, at the vertex. That's an example of a turning point. A graph can have, at most, n-1 turning points. Remember, n is the degree of our polynomial. The last thing that's going to be important to know and is a part of our polynomial graphing toolbox is the end behavior. The end behavior is what happens to our graph as x goes to both positive and negative infinity. Let's go ahead and look at some potential end behaviors. If we let f of x equal a sub n x to the power of n be the leading term of the polynomial that we are graphing, there are four potential end behaviors we are looking at. First of all, the degree, or the power of x, can be either even or odd. Technically, a linear function is a simple example of when n is odd because x would be to the power of 1. Think about what happens on the two ends of a line. You have the opposite behavior on each end. You rise on one side and you fall on the other. Now, think about a function that you know where n is even. That's right, x squared is an example of when the leading term would be of even degree. What happens in a parabola? The parabola has the same behavior on each side. It either both sides go up or both sides go down. Now, in order to determine which behavior happens at each end, whether n is odd or even, we need to take a look at that leading coefficient, a sub n. So the first thing that could happen is if n is odd, so we have the opposite behavior at each end, but the leading coefficient is positive, that means that the graph will fall to the left and rise to the right. Something potentially like this. Notice it is falling to the left and rising to the right. Bet you can guess what's going to happen if we switch the leading coefficient to be negative. Again, think of a linear function with a negative slope. What happens to the left and to the right? That's right, it should actually fall to the right this time. Now, I'm just drawing a generic number of turning points, keeping in mind that you would have to have at most n minus 1. Therefore, the two graphs that I just drew, or two sketches of graphs, could potentially be cubics. Notice they have two turning points, 1, 2. Granted, because it's at most n minus 1 turning points, we could have a polynomial of a higher degree as well, as long as it's odd. Remember, odd degree polynomials are going to have opposite behaviors, so fall and rise, or rise and fall. Now, what about those even degree polynomials? Let's first look at when the leading coefficient is positive. Again, you can always think back on your quadratics because those are the simplest even degree polynomials that you guys already know. What happens if the leading coefficient of a quadratic equation is positive? It opens up. That's right, our graph will rise to both the right and the left. Now, I could draw a general quadratic, or I can make a few more turning points. This has 3 turning points, 1, 2, 3, so it must be at least a 4th degree polynomial, or higher. Now we are on to our last potential end behavior. What happens if we're dealing with an even degree polynomial, but we have a negative leading coefficient? Think about the parabola with a negative leading coefficient. It opens down. Therefore, our polynomial function will look something like this, again falling to both the right and the left. Now, with all of these end behaviors, we can write examples of what are called infinity statements or limit statements. These will be helpful as you move on to higher levels of math, especially when you get to actually dealing with limits in calculus. I'm going to show you just one example, but I would highly recommend that you take the time to write in all of the limit statements for these 4 graphs. For our example, we're going to jump back to the very first one, where n was odd and the leading coefficient was positive. That way, if you want to try and do your own, you can try these 3 after. So the way that limit statements work is they always start with as x goes to blank. In this case, our top one says as x goes to infinity. Remember, here's x, so as it gets bigger and bigger and bigger and bigger, what is happening to y? Well, because this arrow is pointing up, y will also be going to positive infinity. Look at the second one. As x goes to negative infinity, therefore it's going to get smaller and smaller and smaller and smaller, what is happening to y? Our arrow is pointing down, so y is actually also going to negative infinity. Again, take a moment to pause the video and see if you can write the 2 limit statements for each graph of the end behaviors for the remaining 3. Now that we have completed our polynomial graphing toolbox, it's time to move on to the steps to graphing polynomial functions. There are 4 steps, so let's go ahead and get started. The first step is to determine the end behavior. Remember, we only care about the leading term because it's the degree and that leading coefficient that will help us determine this end behavior. Next, we need to find the zeros or the x-intercepts. These values are going to be critical points for our interval chart. Next, we will test values between these critical points to determine the location of graph. That means we will test to see if the graph is above or below the x-axis during each of these intervals. And then lastly, we can combine everything that we know together and complete the sketch of our graph. Remember, you always want to label at least 3 points, which would include any sort of turning point that you know, or test point I should say, because you may not know the exact turning point, in addition to y-intercepts and x-intercepts. Those are all very important points when graphing polynomial functions. Time for us to look at an example. So here's our example. we're going to graph f of x equals x minus 2 times x minus 1 times x plus 3. First step, to determine the end behavior, we would need to actually expand this out. Now, let's be smart about this. Do we actually need to expand it all out? No. In order to get the leading term, we can just multiply the leading term of each of the binomials. So x times x times x, because that's going to be the term with the highest power, or the degree. Remember, with odd degree polynomials that have a positive leading coefficient, we're going to fall to the left and rise to the right. What does this do to help us? Well, when we finish our graph, we want to always double check that it matches what we expected based upon this leading term. Therefore, our graph should fall to the left and rise to the right when we are finished. Next, we need to find the zeros or x-intercepts. This is a really easy one because it's already factored for us. Using the zero product property, we can find the 3 x-intercepts in this cubic function. I get that the zeros will be when x equals 2, 1, and negative 3 from the 3 factors of our cubic function. Now remember, zeros are x-intercepts, which means we can go ahead and put these on our graph right away. Now, because I have my grid lines labeled with the numbers and they're exactly on these where the hash marks meet, they're called, I'm not going to go ahead and label them because it would just be like extra numbers on top. However, if yours aren't labeled, or if any of our x-intercepts happen to be between 2 integers, you'd want to make sure that you're labeling these points because they are important points. Notice, the second part of step 2, these values are critical points for our interval chart. That means we're going to need to create an interval chart next. We've seen interval charts in the past with inequalities. They look like number lines. So let's go ahead and make our number line, putting these critical points on it. There's my interval chart. Now I can move on to step 3, which is to test values between the critical points to determine the location of the graph. Remember, it's usually easiest to first choose 0 if it fits in the interval, and then choose numbers with the least absolute value. The smaller numbers that you're working with, potentially the easier it's going to be, because in general, working with smaller numbers is easier. These are the 4 values that I'm going to test. X equals 0 fits really nicely in this interval, so I'm going to be sure to put that in so that I know my y-intercept. The leftmost interval, I'm going to test x equals negative 4. Between 1 and 2, I'm unfortunately going to have to choose a fraction, so I'm going to do 3 halves. Remember, we really like improper fractions now that we're in algebra, so please do not use mixed numbers. And lastly, up here, I'm going to choose x equals 3. Why don't you guys actually pause the video and solve for y, or f of x, for each of these values of x. As you're solving, you can go ahead and write y equals blank for what you get. Start up the video again when you have them and check to see if your y terms match. Hopefully these are the values you got. Y equals negative 30 when you plug in negative 4 for x, y equals 6 for our y-intercept, y equals negative 9/8 when we plugged in 3 halves, and lastly y equals 12 when we plugged in 3. What does this help us with? Well, because we know the x-intercepts, we know that the graph will not cross the x-axis any other time. Therefore, because this first interval, when x equals negative 4, y equals negative 30, is negative, that means everywhere to the left of negative 3, our graph should be below the x-axis. Similarly, between negative 3 and 1, we know that there's no x-intercepts, and because y equals 6 is the y-intercept, everywhere here, positive, means that it will be above the x-axis. Continuing this pattern, between 1 and 2, we know it's going to be below. And then lastly, greater than 2, we know that the graph will be above. Now, some of these points can actually fit on our graph. For example, this 0, 6 and this 3/2, -9/8 should be able to fit on our graph. Go ahead, put those two on there, and be sure to label them. There's my 2 points. Now, I always get the question of, are these the actual turning points? Do I know that the graph is going to turn at 0, 6 and 3/2, -9/8? Technically, no. But for where we're at in Algebra 2, this is enough information for us graphing the function. Until you get to calculus and can learn something called a derivative, you aren't going to be able to determine the exact turning point of your graph. Therefore, we can just assume that because the graph goes through these, it's going to be close enough to the turning point. Step 4 is then to sketch the graph. So, connecting the dots, I know, for example, that I would need to connect from -3 all the way over to 1. I need to connect from 1 all the way through to 2. And then I need to increase very rapidly from 2 up. Now, you want to be sure that you aren't actually crossing x = 3. The reason why is because we saw here it doesn't cross till y = 12. So I should never actually cross this because I don't go up to 12 on my y-axis. Similarly, when I go down or fall to the left, I need to decrease rapidly, but again, make sure to not actually cross this line here where x = -4. Last step, just double check that it matches what we expected. Because our leading term was a cubic with a positive leading coefficient, we expected it to fall to the left and rise to the right. Our graph falls to the left, rises to the right. So we are done. Very nicely done.